First of all, we are still talking about primitives and group-like elements. And still, the purpose is to prove the theorem about what is the generating function of multiplication. It's a bit of a dead end, I'm afraid, because we're not going to get to use this theorem. But on the other hand, knowing about group-like and primitive elements is useful in itself. And I started the discussion, so I may as well finish it. So that's what we'll do. Now, I spent a lot of time thinking what to do in the remaining class, and my conclusion at the end was that probably the best is to just have an open discussion. So there's not really enough time to completely, well, definitely not to finish the story. And rather than me preparing a lecture about how the story would be finished and without details, maybe it's better to have it as an open discussion. So come prepared with questions, and I will also, and if not, I will take initiative. So basically it will be an open discussion without videotaping, without recording, and it will be both in person and online. So there will be a camera here, but it will only be streaming, not recording. And that's all I have to say about next class, and then expect homework 6 tomorrow. Sorry, but still about next class, so at least we should put in perspective everything that was done, and sort of say what remains and, well, discuss it. Okay. Anyway, let me remind you the definitions we had. So if you have a co-commutative co-algebra, by the way, co-commutative is not crucial for the definitions. The definitions make sense even if the algebra is not co-commutative. I simply don't know examples where it's interesting, where they're interesting, if the algebra is not co-commutative. So I don't know, maybe you could say something interesting even if the algebra isn't, but I care about co-commutative co-algebras. Anyway, so in a co-commutative co-algebra, you can declare that an element is primitive if, well, it's kind of atomic. If when you apply the breakup map that breaks it into two components, it doesn't break. Either it goes full to the left or full to the right. And if the algebra is a Hopf algebra, namely if in addition to the co-structure, to the co-algebra structure, it has a multiplication structure and it's compatible with the co-multiplication, then the primitives make a Lie algebra. And then there are group-like elements. So group-like elements, if you break them, you just get two copies on the two sides. And again, in a Hopf algebra, they make a group. If you have a little bit of experience with Lie algebras and Lie groups, you know that the map that there is a relationship between them, and that if you and the relationship is basically exponentiation. So basically, if you have an element of the Lie algebra and you exponentiate it, you get an element of the Lie group. So my expectation, since this makes a Lie algebra and this makes a group, my expectation is that there will be some relation between the two, and it will have to do with exponentiation. So it's not quite right, but it's nearly right. So let's look into it. So first of all, I want to understand group-like and primitives in the algebras that we care about, so the universal enveloping algebra of Lie algebra G. Yes?
So isn't it necessary to make the group-like elements, say, a Lie group, just a group?
So this is a bit more general. And so Lie groups and Lie groups pertain to finite dimensional. Here the situations are not necessarily finite dimensional, but there are other limitations. You'll see in a moment. Okay? So, yeah. This is not necessarily over the reals. Okay. So, but it is for the bijection between the two things. Not the bijection, whatever, you'll see in a moment, the correspondence between the two things, we need to be able to talk about exponentiation, so it's not about over the real numbers, but it's at least over a field of characteristics zero. Okay, so first I want to talk about group-like and primitives in the universal enveloping algebra of a Lie algebra. So, but you see, to define these things, I only care about the structure of the universal enveloping algebra as a co-algebra. I mean, just to define these things. So, as a co-algebra, well, we still have the ordering maps. So, given a basis, I forgot what I call the order basis. I had a name before. I don't know. Let's call it B for now. So given a basis, we have the ordering map, which is a map from the ring of polynomials in the elements of the Lie algebra, just considered as a vector space, into the universal enveloping algebra. And it's the map which maps x1 to the n1 up to x k, whatever is the dimension, to the nk, to x1 hat to the n1 up to xk hat to the nk. Okay? So, for universal, if you look only in the sense of co-algebras, this is an isomorphism. So, the PBW theorem says that this is a vector space isomorphism, but in fact, even better, it's a co-algebra isomorphism. So, why? So, I guess I want to understand, relative to what structure? Okay, so I have to tell you what is the co-algebra structure on a ring of polynomials. So on polynomials, I have to define just that so if you have the ring of polynomials in some variables x1 up to, well, let's just call, x1 and so on, I'll just define delta of x. Maybe I should have used upper indices. So x1 up to xk. And, but then it conflicts with the powers. Well, I'm not sure what to do. Okay. So I'll just define delta of xi to be xi tensor 1 plus 1 tensor xi and you know what? I made a mistake. I made a mistake in that I don't know whether to put the basis as a subscript or a superscript. And I did a subscript for something else. So let me temporarily invent notation. So you see, if you have the ring of polynomials in x1 up to xk, and you tensor squared it, so my standard notation was to put a subscript for which tensor factor things live in. So temporarily, I'll invent notation and say that this is the ring of polynomials. Well, it's the ring of polynomials tensor itself, but for the second copy, I will use different names for the variables, and then polynomial tensor polynomials are just polynomials in two sets of variables, y1 up to yk. And with this language, delta of xi is xi plus yi. Okay? And I could do the same for the universal enveloping algebra. So the universal enveloping algebra is words generated by x1 up to xk hat, and then the universal enveloping algebra tensor itself will be, so these are, if you want, these are words, so these are words, sorry, this is modular relations. So these will be words in xi hat and yi hat, where xi means you live in the first component and yi means you live in the second component. Modulo, basically the same relations, the same relations as here for the x's, for the xi hat, and then the exact same relations for the yi hats, because I need to be able to, well, because I apply the relations on both sides. And you see, if I regard it as just words in single words, as opposed to pairs of words, then I need a relation, every xi commutes with every yj. So this means that I can sort all the x's to the left and all the y's to the right, and then a word in x's and y's becomes just a pair of words, a word in the x's and a word in the y's. Anyway, in this language, the co-product of xi hat is equal to xi hat plus yi hat. Basically, the co-product for the universal enveloping algebra was defined to be, was defined by this relation. Was defined by the co-product of a generator is that generator in the first component plus that generator in the second component. Anyway, with all of this notation, the co-product here and the co-product here, so the co-product here will map each xi to xi plus yi. So this will become x1 plus y1 to the n1 up to and so on, up to xk plus yk to the nk. This will become x1 hat plus y1 hat to the n1 all the way up to, sorry, times, all the way up to xk hat plus yk hat to the nk. And here the x's are already in order and the y's are already in order, and ordering the x's relative to the y's is free. They just commute. So this is an ordered word. Or so in other words, if you open all the parentheses here and apply the ordering map relative to the x's, tensor the ordering map, meaning relative to the y's, this will simply give you that. Okay, so therefore, understanding group-like and primitives in U of G is the same as understanding it for polynomials. So let's understand them for polynomials. So in the polynomials in x1 up to xk, what does it mean to be primitive? So first of all, let's take a polynomial. Let's take a polynomial f in these variables. What does it mean for f to be primitive? So I'll think of f as a function x1 up to xk, and then delta x, as we agreed, is, sorry, not delta x, delta f is f evaluated on x1 plus y1 up to xk plus yk. Right, this is exactly what delta did. It took a polynomial and replaced it by that. F tensor 1 is you put f in the first tensor factor, so it's f of x1 up to xk, and 1 tensor f is f of y1 up to yk. So, so to say that a polynomial is primitive is to say that f evaluated on. So now let me make a vector out of the x's. So let I don't know what x bar stand for x1 up to xk, and similarly for y bar. Then this says that f of x bar plus y bar is equal to f of x bar plus f of y bar. So this is the condition to be primitive. But you see, this just says that f is linear. This is the definition of linearity. So the conclusion is that f is linear. So f is just a linear combination of the xi's. So f is equal to sum ai xi. And, well, so I've fully understood primitives in the polynomials. But now, what does this correspond to in the universal enveloping algebra? It just means that, so in U of G, primitives are things of the form sum ai xi hat, but that's just linear combinations of elements of the Lie, of basis elements of the Lie algebra. So that's just the whole Lie algebra. So the primitives are simply the elements of jelly algebra. Okay. Now, what are the, so, and it's not surprising because the primitives at the end will make a Lie algebra. So which Lie algebra do they make? The Lie algebra you started from. Okay. Now what about group-like elements? So in polynomials, the relation you have to satisfy is that f of x bar has to be, the co-product of uppercase x. So you know what? Let's call it uppercase f, just not to be confused. And then I want delta f is equal to f tensor f. And delta f is f of x bar plus y bar. F tensor f is f in the first component, so f of x bar times f of y bar times f in the second component. So f should be a function that takes addition to multiplication. If you thought about polynomials a little bit, or power series a little bit, there is only one function that does this, and it's the exponential function. So f must be x, or the exponential of a scalar times this, or more precise, the exponential of a linear function applied to x. Except there are no exponentials in polynomials. An exponential is a power series. So the conclusion is no such f exists, or more precisely, there is only one such f. The only exponential that always exists is the exponential of 0. So other than 1. The exponential of 0 is 1. So 1, the polynomial 1 definitely satisfies that the co-product of 1 is 1 tensor 1. So, okay. But this fails on a technicality. Okay, so the fact that exponentials don't exist is simply because we failed to complete. So we failed to allow power series. Now, had we allowed power series, the answer would be polynomials. Sorry, the answer would be exponentials. However, there is no analog of power series in universal enveloping algebra. It doesn't make sense to speak about to speak about infinite sums inside the universal enveloping algebra. And the reason is that in polynomials, you can speak about infinite sums because you allow yourself to, because these are infinite sums in which the degrees increase and increase. And when you add to power series, different degrees never interact. So you never get to have infinite sums, for example. Okay, the infinite sums happen in different degrees. So you never have actual infinite sums of coefficients to consider. Okay? But the universal enveloping algebra is not graded. In fact, the relation in the universal enveloping algebra is x is the defining relation is x1. Well, x and y are not the same as here, so maybe I'll call it uv minus vu is equal to u bracket v, and these are words of length 2, and this is a word of length 1. So the relation mixes lengths of words, so you can't just say it's graded by the length of a word. So the way out is to allow, is to insert another parameter as the power series parameter. So so if you look at the universal enveloping algebra of a Lie algebra G, and you look at power series in another parameter, so these are power series in H bar whose coefficients are elements of the universal enveloping algebra. This is isomorphic by degree, simply, by coefficient. So you look at each coefficient of H bar is a copy of the universal enveloping algebra. So it's isomorphic to Q of the Lie algebra with H bar added. And here you do have exponentials. So here you can write e to the H bar times any linear combination of the generators. And in fact, you don't need to write H bar. You can write here any power series whose leading term is 0. Because if the leading term is 0, then when you exponentiate, you get higher and higher powers of H bar, so the summation terminates in every specific. So let me write it. So basically, so this belongs here, but also the exponential of sum of AI of H bar times Xi, provided AI of 0 is equal to 0. Because then it means that AI starts with H bar, and when you exponentiate, you get higher and higher powers of H bar. So at every specific power of H bar, it's a finite sum. So as a power series in H bar, it's convergent. But now this gives you this gives you group-like elements in UG of H bar, namely things of the form exponential of sum AI of H bar Xi hat with the same condition on the AI. So these are the exponential of, these are the group-like element in this algebra. So it's not quite the, so in the original algebra it wasn't true, but that exponentials are, that group-like elements are the exponentials of primitive elements. But if you allow an extra parameter, it becomes true. Okay. And again, with some condition. So AI of 0 is, so not every primitive element can be exponentiated, but the primitive elements that start with, that are zeros, that don't have a constant term relative to H bar, can be exponentiated and are in one-to-one correspondence with the group-like elements. Okay. So the next thing is to say, so in...
Quick question.
Oh, wait. Sorry, I was wrong. I'm wrong. I'm completely wrong. Exponentials here don't go to a, the map here is the ordering map. To go from here to here, I use the ordering map. the ordering map does not preserve the property of being an exponential. Sorry. So once you are here, you're exponentiating non-commutative things. So sorry. So what I should have. Sorry, I'm blundered. What I should have said. There are group-like elements in the universal enveloping algebra, but they are of this form. They are of orderings of. Well, sorry, and now I need to remove the hat. They're simply the images via the ordering map of the exponentials here. Yes?
Yeah, I'm not sure why the AIs are functions of H bar.
Because in the group, in the ring of polynomials over power series in H bar, the primitive elements are linear functions of the generators. So of the variables. But the linear functions, but now we're allowing power series. So the linear functions can be power series in H bar. Okay. Okay. So now theorem, and this is somehow the key theorem. I claim that in U of G with H bar added, there is a bijection between, so group likes are exactly exponentials of primitives. So, and this is at the end the theorem I want to prove. I want to show that, well, that this is an exponential of a primitive. Sorry, I was silly to just say it, but I mean, that's somehow the whole point. So, in UG of H bar, primitives, group-like elements are in a bijection, or are the same, it's just the same, as exponentials of primitives. I suppose I need the extra property with or which vanish, that vanish mod H bar. So if you look at their constant term, the term with no H bar, you get 0. You know, sorry, again, I'm so silly making the mistake here. Again, just to be clear, what is this? Okay, this is e to the ai h bar x1 times, so you see, in the commutative world, the exponential of a sum is the product of the exponentials, and then I order it. So I just get e to the ai h bar xi times e to the ai h bar x1 times e to the a1, and then a2 x2 times all the way up to e to the a k of h bar xk, and that was exactly the type of product that I had when I was talking about the multiplication, about multiplying two exponentials. So it's exactly this that I want to show is a single exponential. Okay. So somehow I completely missed the point. Anyway, proof. So, okay, one direction is easy. So, suppose you have a primitive. So, if x is primitive and x mod h is equal to 0, then e to the x. So first of all, e to the x makes sense because since there is no constant term, I can exponentiate. And now I can compute the coproduct of e to the h. And since the coproduct is an algebra morphism, this is e to the coproduct of x, which is e to the x tensor 1 plus 1 tensor x, which is e to the x tensor 1 times e to the 1 tensor x, because the things that happen in different tensor factors commute. But this is e to the x tensor 1 times 1 tensor e to the x, but this is e to the x tensor e to the x. So one direction is easy. The other direction is a bit harder. So assume we have a group-like element, so it satisfies delta of x is equal to x tensor x. And assume, okay, so what I'm going to try to do is to construct a primitive element such that, so I need, well, okay, I need an x such that uppercase x is equal to e to the lowercase x. Now, everything here is happening with a parameter h bar. So everything is happening over power series in h bar. So uppercase x is a power series with coefficients elements of the universal enveloping algebra, and so is the right-hand side. Okay? So what I'm going to do is I'm going to construct x degree by degree in h bar. So I'm going to try to solve this equation to find lowercase x, which works. So I'm going to find a lowercase x that works for higher and higher powers in h bar. So assume I've succeeded to degree k. So assume x is equal to e to the xk modulo h to the k plus 1. Or in other words, 2 h to the k. So all the powers up to power h to the k match, and if you mod out by h to the k plus 1, it doesn't match. Okay? So I need to find the next degree in xk. No. Even before that, I need to start the induction. So I need to find x0. Okay? But you see, modulo, so suppose I'm looking, so suppose I start this. So I want to start this. I want to find this. I want to find x0. So I'm looking modulo h bar. If I mod by h bar, then all that is left is the universal enveloping algebra itself. Right? If it's the same as setting h bar to 0. Oh, it's not the same, sorry, but I mean, if I mod out by higher powers of h bar, I'm just left with the coefficient of h to the 0, and the coefficient of h to the 0 is the universal enveloping algebra. So, assuming x is a group-like element in the universal enveloping algebra itself, I need to find x0. But there are no group-like elements in the universal enveloping algebra, except for one. So the conclusion is that at k equals 0, x0 must be 0. So at k equals 0, we set x0 to be 0, which is fine because we wanted primitives that vanish modulo h bar, but that's exactly what this means. Okay. So now assume I found this, and I want to find the next. So this means that if I look at at uppercase x, if I look at uppercase x and multiply it by e to the minus xk, so e to the minus what I found so far, then this is equal to, well, these two are equal up to degree k. So this should be 1. If they were equal all together, you'll get 1. Right? Sorry, if x was e to the xk, and you multiply by 1 minus xk, you'll get 1. So you get 1 up to degree k, including. So you get 1 plus h to the k plus 1 times y. And I claim that y is primitive. Indeed, let's compute the coproduct of x times e to the minus xk. So this is the product of group-like elements, and the product of group-like elements is group-like. So this is equal to x times e to the minus xk tensor x times e to the minus xk. And this is equal to 1 plus h to the k plus 1 y tensor 1 plus h to the k plus 1 y. But you see, this is also equal to the coproduct of this. So it's also equal to 1 tensor 1 plus h to the k plus 1, the coproduct of y. So now compare powers of hk. So in the coefficient of h to the 0 is 1 on both sides. The coefficient of h to the k plus 1 is y here, and y tensor 1 plus 1 tensor y here. So the conclusion is that the co-product of y, sorry, the coefficient of h to the k plus 1 here is box, so is the co-product of y. So the conclusion is that delta of y is y tensor 1 plus 1 tensor y. Sorry, I should have said y is simply an element of the universal developing algebra. So y is primitive. Okay, so I can set x to the k plus 1, xk plus 1 to be xk plus hk, h to the k times y. Well, I took a primitive things and added a primitive things to think to it, so this is still a primitive. So this is still primitive, right? The equation to be primitive is a linear equation. Well, I erased it, but it's a linear equation. So this is still primitive, and if I now look at, if I compare x with e to the minus xk plus 1, so if I compare x with e to the minus xk plus 1, I'll get x times e to the minus xk okay, y does not commute with xk, so it's not trivial. So let's do it modulo h to the k plus 2. So wait, how do I want to do it? You know what? Let me do something else. So modulo h to the k plus 2, let me compute e to the xk plus 1. So this is sum xk plus h to the k y to the power m divided by m factorial. And the first okay, up to h to the m, sorry, up to h to the k, sorry, no, I want to go, yeah, modulo, yeah, so I want to look at powers of, sorry, I'm confused. What am I doing? Oh, sorry, I'm stupid. This is h to the k plus 1, right? The whole point was to add an h to the k plus 1. I'm sorry about that. Sorry. So up to the, so if you exclude h to the k plus 1, if you up to power h to the k plus 1, this doesn't even contribute. So modulo h to the k plus 2, this is e to the xk plus 1, and then in power, in degree h to the k plus 1, sorry, this is e to the xk, and then in degree h bar, in degree k plus 1, you get two contributions. You get one contribution from xk to the k plus 1, and another contribution, so this is still included in what I wrote here, and another contribution from here. So the other contribution is sorry, the only other contribution comes from the degree 1 piece in this expansion, where you take, so basically, what am I doing? Okay, let me say it differently. When you open parentheses here, every term that includes two or more hk to the 2 or more of the y's will vanish because it has h to the k plus 1. In fact, every term that has both an x and a y will vanish because you have h to the k plus 1 here, and you have at least one h bar coming from xk, because xk has h bars in it. So so the only contributions are contributions in which you get only x's, and that's e to the xk, and the term in degree 1 in which you take only the y. Because again, if you have if you're taking both an x and a y, you get 0. So this is the only new contribution is h to the k plus 1 y. Did I do it right? I hope so. But that means that exactly kills the. Sorry, I'm out of time, but that exactly kills this one. So if you look at x e to the minus xk plus 1, you get x times well, you just the plus becomes a minus, and you get e to the negative xk minus h to the k plus 1 y, and that term will cancel that y. So you'll get 1 mod h to the k plus 1. Oh, this is terrible. I'm sorry. Well, so the conclusion, so I'm running way over time, and I'll just say in a few words. No, so well, the conclusion is that, the product of group-like elements is group-like, and group-likes are exponentials of primitives. So the product of any exponentials of primitives is again an exponential of primitives, and that's what I wanted to show. I needed to show that some product of exponentials was again a product of exponential, was again could be written as the exponential of a product of things that are linear in the variables, namely primitives, and that's been shown. The small problem is that sort of I'm working with the wrong ring, but it's a minor issue. So instead of power series in H bar, you consider power series in all the Greek letters, and you get the same result. And I still need to show that the representation that was faithful on primitives is faithful on group likes. Well, I definitely cannot do that. So I'll stop. And I'm sorry, and see you on Wednesday.